Yes, sir.
So friends, what we have done in the two kind of motions that we have discussed here. One was the projectile motion, where we obtained the relations for the range, for the maximum height, and for the time of flight of the projectile related to the angle of projection, etc., etc. And I told you that there are two kinds of motion. One is along the horizontal axis and the other was along the vertical axis. The motion here in the horizontal direction was without acceleration, and the motion here was with an acceleration, which was taken as, and if the direction of the y-axis is taken this way as positive, then the value of this g was taken as approximately equal to, I suggest that you take it as minus 10 meters per second square, so that the calculations are fast. So after deriving all these equations related to this, I discussed with you the uniform circular motion in a horizontal circle, wherein we obtain several things associated with it for the motion, and I took purposely the positive direction of the motion with respect to the center and the radius associated with it, and then I had the r vector, that is r theta, r at a time t, okay, which could be described in terms of two motions, one in the horizontal direction, the resolved parts, another in the vertical direction, and this is the magnitude of this motion was taken as a, so a cos of omega t plus phi and a sin of omega t plus phi, where omega is the angular velocity. I defined all those things. I obtained the relation for the velocity, which was related and which was supposed to be at 90 degrees particularly. So this was v theta, or v at a time t, and then correlated to that there was an acceleration. This acceleration was towards the center, called the centripetal acceleration, and it made an angle of 90 degrees. This one, there was another angle of 90 degrees over here. So all these things have to be taken into consideration. The value of a was, the values of a, v, etc. in terms of r were derived, and I also told you as to what is the how come these things are related with each other. To augment that, to substantiate that, to make it more vivid to you, I am taking a set of questions which are only representative. In fact, today I will tell you about 5 questions, how to deal with them, but I suggest to you that you must take up between 50 to 100 questions definitely, and repeat that at regular intervals of time so that it is afresh to you. So the first question that I take, which is appearing here, okay, on the screen, and I read it for you. If the seconds hand of a clock moves with a uniform angular speed and its length is 10 centimeters, calculate its, number 1, its angular velocity, and number 2, the speed of the tip of the seconds hand. Okay, so look here. when you read this question, I told you the method is that we must be able to say the question in our own words, and we make some sketches for that. So I just make a quick sketch of it, and then I have the hands, minute hands, okay, I'm sorry, the seconds hands. So I'll write seconds hand. You know that in a watch it always moves in the counterclockwise direction, and when it completes an angle of 2 pi radians, which is 360 degrees, then we say that one rotation has been completed. So you can see in this case I will write about the time of one revolution, and the time of one revolution is 60 seconds. Okay, 60 seconds. So I can write that because the corresponding theta, the angle, is equal to 2 pi radians. This is like small c and half of the circle, which gives us the representation of the radians, 2 pi radians. Okay. Now, angular velocity. Angular velocity is omega. Angular velocity is equal to omega is equal to how much? Because we have theta is proportional to t, and this is equal to theta upon t. Whatever angle has been traversed in a time t, that will give us the angular velocity, and this will turn out to be, in our case, theta is equal to 2 pi upon 60 radians. Radians, I'll rather write it like this, radians per second. So I have a picture, a mental picture of this. So the angular velocity is equal to pi by 30 radians. I'm not going to solve that for you. Pi is 3.14, and in most of the situations these days we are not given a calculator, but we have to make calculations, estimations without using calculator. In our days, when I used to be a student, at that time we used to be provided with a log table, and the calculations used to be done using log tables. Okay, so the speed v of the tip of this seconds hand, this all depends upon, because 2 pi radians, uniform angular speed, and its length was given as 10 centimeter. So I'll write this length over here for big clock that we have. So this is equal to, V will be equal to omega into R. Omega into R. The R is known to us. The omega has been calculated already. I'll just substitute those values. Pi over 30 radians per second. Radians per second multiplied by R, which is 10 centimeters. But I'll write that 10 centimeters as 10 upon 100 meters, because each meter has got 100 centimeters. So this turns out to be equal to 10 upon 100. What will the unit? The unit will be meter. Now radian is just a number. So I'll find that this will turn out to be equal to pi upon 300. meter per second. So this is how we are going to calculate. We have calculated the velocity of the tip of this thing. Also, like in another example, somebody can ask, what will be the velocity of this point, which is say 2 or 3 centimeters away from it? So all we have to do is to substitute the value of nu r, because for this point also it goes in the same circular motion, in the same direction. Of course, the velocity vector is different. It is 0 over here, and it is here, the value is v. So in between you can think of it how the value of the velocity will be calculated. So this is the solution, and now we come to problem number 2.
Yes, sir.
Oh, there has been a big mistake. The clockwise motion takes place like this. It's not anti-clockwise. So the clockwise motion is taken like this. And so the rest of the problem can be solved like this only. The only mistake that I made, I was taken for a right, and this motion which I am showing over here, this is the direction is like this, and here also the direction is reverse. The direction here also is reverse. There is a clockwise thing which works for a clock. That is why it is called clockwise. This is the motion under consideration. Now we go to question number 2.
Yes, sir.
Question number 2, which is appearing, you can see, you can read it, and I will read for you. An artificial satellite. Satellite is something which goes around the earth. There is an artificial satellite, takes 2 hours to complete its circular revolution around the earth. What is its angular velocity? Very simple question. If its distance from the center of the earth is 10,000 kilometers, estimate its speed. So I again make the satellite is going around the earth, maybe anyway, clockwise or anti-clockwise, and this is the earth. So it is quite far away from the earth, and this is the earth's radius, this is the radius of the satellite, and this is 10,000. I'll show it to me. I'll read it again from there. This is 10,000 kilometers. I'll rather here itself I'll put it into meters. So this is 10,000 into 10 to the power of 3, because each kilometer is equal to 1,000 meters. And so using the law of indices, this I'm writing for you as 10 to the power of 4 into 10 to the power of 3 meters, which is equal to 10 to the power of 7 meters. Okay, so I've just changed the given value in kilometers into this, and then the satellite takes how much time? The time of revolution, that I'll write here, the time of a revolution is equal to 2 hours, which again I must convert right now into minutes, and those minutes into seconds straight away. So this is 3600 multiplied by this, which turns out to be equal to 7,200 seconds. This is the time period that we get. So now because theta is proportional to t, so omega, you know that you need not remember this value of omega is equal to theta upon t. What you need to remember is, and scribble it fast, that theta is proportional to t, the angular displacement, and theta is equal to omega t, and therefore this relation is readily obtained, that omega is equal to theta upon t. Okay. Now this theta again, how much is? Theta is equal to 2 pi radians. So this is equal to 2 pi radians upon the time, which is 7,200 seconds. So I can write it as pi upon, I'll not substitute the value of pi, 3600 per second, or radians per second. Remember that the radians is a dimensionless quantity, and therefore we can substitute it like that. So it is 10 to the power 7 meters and pi upon 3600. Now the velocity of the projectile here, this is the velocity of the projectile, and this is equal to r into omega r, whatever you want to write, r into omega, which is equal to, now r is how much? 10 to the power of 7 meters, into pi by 3600 radians per second, or per second, radians per second. So this turns out to be equal to, if I just take these two zeros away, then 10 to the power of 5 meters and pi by 36. This is pi upon 36. If need be, you can make the calculation, else you can write it as 10 to the power of 5 meters per second. Of course, you can be asked the value in terms of kilometers per second, which also you can calculate by dividing this quantity by 10 to the power of 3. Okay, so this is how, in certain steps, what we have done, we have made a sketch. What we have done, we have substituted these values without writing r and this and that. By the way, the radius of the earth is 6400 kilometers. Okay, so it is much above the surface of the earth. Normally when we will talk about that, satellites which are very close to the earth, their radius or their distance from the center of the earth is taken as equal to 6400 kilometers, with 6400,000 meters. Okay, so that is how. Now we go to the question number 3. So question number 3, as it is, I read for you. A point mass, yani a body, a point mass m is moving in a horizontal circle of radius 2 meters with a speed of 10 meters per second. Compare the centripetal acceleration with the acceleration due to gravity, which is the gravitational field is taken as 10 meters per second square, we are asked another question there. What is the angle between the directions of the two accelerations? What is the angle between the directions of the two? Okay, so point mass on a horizontal circle. Now let us make horizontal circle a representative diagram, free flow of your hand, and the radius is taken as from here to here, it is 2 meters. I make this over here. This is the radius of the horizontal circle, and the point mass, I am taking a point mass, and in the question it is written m. Of course, there is a speed. I again go in the anti-clockwise direction, okay, and the speed is, yani, the magnitude of the velocity vector has been given to us as v is equal to 10 meter per second. 10 meter per second. Okay, so this is the information that we have. Now they say that there is a centripetal acceleration. I show the centripetal acceleration as leading this by an angle of 90 degrees, and therefore centripetal or center seeking. So I must write that this is my A, and I must write that this is my V. Okay, the two vectors. And in the calculations that we have, and you will remember it, that A is given as A is equal to V square upon R. Okay, A is given as V square upon R. Of course, we can substitute the value. V square 10 into 10 divided by, this is the velocity meter per second, and the R is given as equal to 2, okay, meter. So this turns out to be equal to, after the calculations are done, this is 50 meter per second square. This is the centripetal acceleration and of course, even if it is a circle, then we must have and if this is the horizontal circle, then I will show that this is the direction of the g vector is into the board. Okay, so into the board, like this, and there is an acceleration vector which is like this. So the two are making an angle of 90 degrees with each other, and the value of g, the magnitude of g, this is equal to 10 meter per second square, and therefore the ratio A is to g of the magnitudes of these accelerations. This is equal to, being a good boy, I can write it as 50 is to 10, that is 50 upon 10, which is equal to, I can say that this is equal to 5 is to 1. But 5 times the acceleration is like this, and the angle between the two of them, the theta here, theta, the acceleration is this way and the value of g is this way, and therefore the angle is equal to theta is equal to 90 degrees. This we simply know from our knowledge that the acceleration will always be 90 degrees with velocity, and one is the acceleration here, for example, is like this. Then on this board I am showing to you, then the value of g will be downward in this direction, and therefore we are able to solve the question. Now going to the next question, which appears on your screen.
Yes,
So we have question number 4, which is a related question, and it is also about an artificial satellite. What we read is like this: time taken to complete a circular orbit close to the Earth's surface by an artificial satellite of the Earth is 90 minutes. The time taken is 90 minutes. Obtain the acceleration of the Earth's satellite and take the radius of the Earth equal to 6.4 into 10 to the power of 3 kilometers. By the way, I would like to make a remark about the previous question, where I said that the particle of mass m is moving. That is irrelevant to the solution. It's not important. This is the data that could be avoided, because whatever is the solution is true for any value of the mass of the body under consideration. The only thing is that the body has to be taken as the point mass. Okay, so this question, again, like a good boy, I start with the circle and I just draw the radius, which I may substitute for the Earth, equal to 6.4 into 10 to the power of 3 kilometers, okay, which of course is equal to 6400 kilometers, and therefore I can write this as 6.4 into 10 to the power 3 plus 3 is equal to 6 meters. So I have made a point for me for this question: 6.4 into 10 to the power of 6 meters. Here I would like to tell you something, that normally whenever these powers of 10 are used in describing any scientific number, we always take it like I cannot take it as 64 into 10 to the power of 5, 640 into 10 to the power of 4. No, always we take as 6.4. So we just must make a habit to be scientific. And in this case, the other thing is that the time for, I can write without showing it here, the time is equal to the time for one revolution which it takes there is 90 minutes. 90 minutes, which again I can change into seconds. So 90 into 60, I'll write here and it's easy. Now 6 9s are 54, 00 second. Okay, so I have just converted in a scale down to the value, which is 5400 this. Now I have to calculate the value of A, which is the acceleration towards if the body is here right now, and this is basically very close to the surface of the Earth. Okay, so this is having, so the acceleration is towards the center, and this acceleration is a, and we have to find out the value of this acceleration, which will be equal to v square upon r. From the formula that we know, v square upon r, which is equal to omega r whole square divided by r. So this will become equal to r omega square. Okay, I can write it as r, one r will cancel, r omega square, and omega will calculate as 2 pi nu. Omega is equal to 2 pi into nu, which is the frequency, the angular frequency, and the frequency. This is equal to 2 pi upon capital T, 2 pi upon capital T, radians per second, which is equal to 2 pi upon 5400 per second, and radians per second, per second, doesn't matter at all. Okay, so omega value is here with me, and the value of r is 64 into 10 to the power of 6 meter. So I can substitute this value, 6.4 into 10 to the power of 6 meters, and into 2 pi whole square, this divided by 5400 squared. Now pi square, I told you that the pi square is equal to how much? Is taken as approximately equal to 10. I told you this, so I can substitute this value over here. This will turn out to be equal to 6.4, and from here I'll get 4 into 4 into 10, and that will make it 10 to the power of 7 upon 5.4. I'm just testing your prowess, whole square into 10 to the power of 6. Am I right? Just think, because this is I've taken as 5.4 into 10 to the power of 3, so 10 to the power of 3 goes like this. And if I just take this into consideration, then this is 6.4 into 4 upon 5.4 squared, and 5.4 into 5.4, of course, and this is the whole thing multiplied by 10. And if we work out the arithmetic, if I work it out, then it appears to be approximately 8.7 meter per second square. So this is how the calculation is done for a very simple question that has popped up on your screen. Okay, now we take up the last question. So question 5, as it pops up, I read it for you. The length of a propeller blades is 5 meters. If the propeller rotates at 600 rpm, that is revolutions per minute, determine the tangential velocity of the blade's tips. Also, find the velocity of a point once the point on the blade halfway between the tip and the axis of rotation. Halfway between the tip and the axis of rotation. So once again, many things are given to us. Okay, I will make the representative diagram. Okay, that this is the length of this is 5 meters. So this is the tip of the propeller blade, 5 meters. And then if the propeller, half the thing as I have given to you, that the halfway mark on the propeller, okay, that will be here 2.5 meters, halfway. Any value can be given to us. So we'll see as to what is the thing that we obtain. So the diagram is ready for us. The propeller goes like this, 600 RPM. So I'll write 600 RPM per minute. Okay, so I'll get this as equal to 600 in 1 minute. We have 60. Okay, so seconds, so this is revolutions per second. This is equal to 10 revolutions per second. 10 revolutions per second. This is what we will calculate readily in a nutshell, and then we can calculate as to what is the value of omega, the angular velocity. The omega, the angular velocity, okay, this is equal to nu. What we have estimated here from RPM, we have estimated the value of nu, okay, the frequency. So we have omega is equal to 2 pi into nu. The nu turns out to be 10 revolutions per second. So this will be equal to 2 into 10 into pi revolutions, okay, or radians per second. Okay, so omega is obtained, and this is equal to 20 pi. 20 pi, the value radians per second. I can just write it quickly. So the velocity at the tip, velocity as the tip will be equal to, because the formula is that this is equal to r into omega, r into omega. So this turns out to be equal to, r is 5 meters, so 5 into omega, which is 20 pi, okay, which is equal to, now you can go, it's 100 pi, meters per second. And of course in the end, now you know that the value of pi is 3.14, so you can just multiply it by 100. It's very simple, 300 and 14, 314 meter per second. Now halfway through, what we have to do is V of the point halfway, HW I'll just write, just to distinguish it, is the value of R at the halfway into omega. Omega does not change, omega is the same. Whether for all points on this propeller, all points, the value of omega is the same. So this I'll write as 2.5 into 20 pi, and finally I calculate this as equal to the final value I'll get, divide this value by 2, and I'll get 157 meter per second. So that gives us an initiation into the problems of circles. The circular motion associated without an acceleration associated with it. Now, of course, we have done just 5 representative problems, and I suggest to you that from any books that you have, okay, you must be able to do many more questions, and you may become sort of a mini master for that. With that, we come to an end of doing this chapter, and because we have to do more, so from kinematics, where we have only 2 dimensions of the length and time, and associated things, for example, which are the displacement, velocity, acceleration, average, instantaneous, okay, and then the radial velocity, the angular velocity, the centripetal acceleration, etc., etc. It's all over. So now we'll talk about, we'll go into a new domain, and I will talk to you about the laws of motion, and with that we'll come to the concept of inertia, the concept of momentum, the concept of rate of change of momentum associated with force, etc., etc., and the 3 laws of motion, of which the first law is stated to be by Newton, but interestingly this law existed, and this was proposed, as the Europeans say, by Galileo, and as I have had a talk with some Arabic scholars, and they say that this law was discussed in the 1st century after Hijrah, etc., etc., and of course in the rich tradition of the Indian rishis and munis, similar laws, things existed. So we are in the evolution of science, which is dated by the Europeans to be the time when Galileo challenged Aristotle's method of doing. And remember, in the first lecture I told you that Aristotle challenged Plato, Aflatun, and he was challenged by many classmates and other contemporaries, and then you remember what he said? He said, Plato is dear to me, but dearer still is the truth. So he abandoned Plato. The great Arabs adopted him for certain things, rejected many things, put in new things in the Oriental Renaissance of science. Then when Europe came out of the Dark Ages, then Galileo challenged Aristotle, and we got the law of inertia, etc., etc. So things change. Sometimes you never know when the Italians are ahead of the British, when the British are ahead of the Germans, who contributes. But the thing is, Italians, Germans, French, Indians, Arabs, they are all humans. So who contributes to the progress of science? It is the humans, it is the humans, it is the humans, it is you, it is you, it is you. Thank you very much. So wait for that.